Hello everyone, and welcome back to the Explainer. Okay, let's dive into this. Today, we're taking something that might initially look like a bunch of abstract math on a whiteboard, and we are going to completely ground it in the real world. We're unpacking a really brilliant lesson plan centered around finding the distance and midpoint on the Cartesian coordinate plane. Basically, we're going to see how flat grids and number lines are actually the secret underlying language behind how we navigate our neighborhoods, build our houses, and even map out our digital worlds. So grab your mental compass because we have a genuinely exciting journey ahead of us today.
Here is our roadmap for today's Explainer. We'll start with mapping our world, move into plotting on the grid, figure out finding the distance, learn about meeting at the midpoint, and wrap it all up with some real-world applications.
All right, Part 1, Mapping Our World. If you have ever looked at a map of a city or even just glanced at a digital GPS layout on your phone, you're essentially looking at a Cartesian coordinate plane. I know that sounds like heavy algebraic jargon, but think of it simply as a two-dimensional surface formed by two intersecting number lines. You have this horizontal line running left to right, that's the x-axis, and you have a vertical line running up and down, that's the y-axis. I want you to picture those intersecting axes exactly like the main crossroads in your local barangay or neighborhood. Everything north, south, east, or west of that main intersection can be mapped out perfectly. These lines create a super reliable structured grid that lets us pinpoint exact, precise locations anywhere on that surface. Without this foundational grid, giving directions would honestly just be guesswork, right? We'd be relying on vague landmarks instead of exact, reliable measurements.
To make this incredibly practical, we're going to anchor our entire explainer today around one specific contextualized problem straight from our source material. I want you to imagine a learner's journey. You're starting out from home, which we're going to plot exactly at the coordinates -1, +3. We'll call that h-1, 3. Now your destination is the ALS Learning Center, which is located at coordinates +3, -1. We'll call that L3, -1. Throughout the rest of this explainer, we're going to figure out exactly how to map this specific route, measure exactly how far you have to travel, and eventually figure out where you can meet a friend halfway.
Let's keep moving. Section 2, Plotting on the Grid. Let's move to and see how this builds, because to plot anything at all, you really need to understand the basic anatomy of the grid first. We already mentioned the x-axis going horizontally and the y-axis going vertically, but where those two main streets cross right in the dead center. That is called the origin, perfectly sitting at 0, 0. These crossing lines essentially divide our map into 4 distinct sections, which are known as quadrants. But here's where the real magic happens, the ordered pair. Written as x, y in parentheses, this is literally your absolute set of instructions. The first number always tells you how many steps you need to walk left or right on that horizontal x-axis. And the second number? It always tells you how many steps to walk up or down on the vertical y-axis. It's a precise, totally unambiguous address for any single point in space. So let's test that out with a quick formative assessment from the lesson plan just to ensure the mechanics are crystal clear. You gotta think about starting right at that center origin every single time. Take point A. The x-coordinate is 2 and the y-coordinate is 3. That means you start at the center, walk 2 steps to the right and 3 steps up. Boom, you land squarely in the upper right, which is quadrant 1. Now consider point B, -4, 1. That negative x means you actually walk left 4 steps, then up 1, landing in quadrant 2. Point C is a little tricky, check this out, 0, -2. Since x is 0, you don't move left or right at all. You literally just walk straight down 2 steps, meaning you're sitting right on the y-axis itself. And finally, point D, 3, -3. That takes you right 3 and down 3, placing you in the lower right, quadrant 4. Really understanding this exact plotting mechanism is absolutely crucial so no one gets left behind before we introduce the slightly heavier math.
All right, Part 3, Finding the Distance. So, if we want to know the exact straight line distance between 2 points on our map, we can't always just count the grid squares, right? Especially if the line connecting them is diagonal. For that, we have to use the distance formula. Now, I do not want you to be intimidated by this equation. Let's just step through it slowly together. Step 1, simply label your 2 locations. One location is your first point, so it gets the labels x1 and y1. The other is point 2, so it gets x2 and y2. Step 2, substitute those numbers right into the formula. The formula states that distance, or d, equals the square root of a specific calculation. You take the quantity x2 minus x1 and square it. Then you add that to the quantity y2 minus y1 squared. What you're basically doing here is finding the total horizontal difference between the points, squaring it, finding the total vertical difference, squaring it, and then adding them up. Step 3 is just simplifying that basic math and calculating the square root at the very end. It's essentially like a reliable cheat code to unlock the exact measurement between any two places.
Now, what's really interesting about this slide is how beautifully simple this becomes when we actually apply it to our real-life journey. Remember our starting point? Home at h-1, 3, and our destination, the Learning Center, at L3, -1. Let's just plug those exact numbers in. Our x2 is +3, and our x1 is -1. So the first part of the calculation is 3 minus -1. And remember, when you subtract a negative, it transforms into a positive. So that's actually 3 plus 1, which is 4. And 4 squared is 16. Easy enough. Now let's handle those vertical y-coordinates. Our y2 is -1, and our y1 is +3. So that is -1 minus 3, which gives us -4. Now what happens when you square -4? Well, a negative times a negative is a positive, so that is also exactly 16. So look at that. Under our square root symbol, we just have 16 plus 16. That equals exactly 32.
Which leads us to the grand reveal. The exact straight-line distance from home to the ALS Learning Center is the square root of 32. Now, in a formal math class, you'd probably simplify that radical to 4 times the square root of 2. But honestly, if you were measuring this out on a real-world map or just putting it into a standard calculator, that comes out to approximately 5.66 units of distance. By just breaking down that formula step by step, we took 2 totally abstract points on a grid, plugged them into our mathematical tool, and successfully calculated the precise, indisputable distance between them. Pretty cool, right? This brings us to a highly practical scenario. Okay, so we know the total distance of the journey is about 5.66 units. But what if a classmate is starting out at the Learning Center and you are starting at home and you guys want to compromise? What if you want to meet exactly in the middle, saving both of you some travel time? How do we figure that out?
That brings us to Section 4, meeting at the midpoint.
While the distance formula we just looked at is all about measuring total length, the midpoint formula is entirely about finding balance. And honestly, it's actually much more intuitive than you might think. I want you to think of it simply as finding the mathematical average of your locations. Step 1, you take the 2 x-coordinates from your points, add them together, and divide by 2. You're literally just finding the average horizontal location. Step 2, you take the 2 y-coordinates, add them together, and divide by 2. Now you're finding the average vertical location. Step 3, you just take those 2 results and put them back into an ordered pair with parentheses. That new pair of coordinates, that's your exact halfway point. You are quite literally just finding the middle ground between 2 extremes.
So let's test this average finding method on our specific journey. We need the halfway point between home at h-1, 3 and the Learning Center at L3, -1. Step 1, let's add the x values together. -1 plus +3 equals +2. We divide that 2 by 2 and we get 1. Simple enough. Now for step 2, add the y values together. +3 plus -1 also equals +2. We divide that 2 by 2 and again we also get 1.
So, the crucial point is when we express our results as a new ordered pair, we get 1, 1. That specific point is the exact mathematical center of your route. Think about it. If you walk from -1, 3 to 1, 1, and your classmate walks from 3, -1, up to 1, 1, you will have both traveled the exact same distance. You're going to be shaking hands right in the exact middle of the coordinate plane. It completely, 100%, takes the guesswork out of meeting up.
And just to prove that this wasn't some lucky break with easy whole numbers, the source material actually provides data from a formative assessment to back this up. For instance, between point A at 1, 2 and point B at 4, 6, applying our formulas shows a precise distance of exactly 5 units, with a halfway meeting point at 2.54. So even when the averages result in decimals, the grid stays completely reliable. And if we test points C and D, jumping across entirely different quadrants with negative numbers, the calculated distance is again exactly 5 units, and the midpoint lands right on the y-axis at 0, 1.5. These mathematical rules, guys, no matter how much the numbers change or jump across the map, they work with absolute reliability every single time.
And that takes us to our final section, real-world applications.
And this brilliantly illustrates that the Cartesian coordinate plane is not just ink on paper, it's literally the underlying architecture of modern life. When urban planners map out new barangay routes or design complex city infrastructure, they are heavily relying on these exact distance formulas to ensure roads are efficient and spaces are optimized.
When an architect or builder is planning construction layouts, plotting corners on an invisible grid ensures the building is perfectly square and that the physical measurements align flawlessly with the blueprints. In professional sports, coaches and analysts map out field positioning using similar grids to determine the absolute optimal distance between players on a pitch or a court. And honestly, arguably the most relevant to our daily lives today, every single time you order food from an app or use a digital GPS in your car, algorithms are rapidly calculating millions of distances and midpoints between coordinates on a massive digital grid. It uses this precise logic to tell you exactly when your delivery driver will arrive or where your next turn is. The abstract math you see on a whiteboard is the exact same math running our digital world.
As we wrap up this explainer, I want to leave you with a thought that takes these mathematical concepts and makes them just a little bit more personal. The distance and midpoint formulas inherently prove that no matter where you start your journey and no matter how far away your destination might seem, there is a clear, mathematically measurable path between them. So, if your entire life and your biggest goals could be mapped on a massive coordinate grid, what's the midpoint between where you are right now and where you want to be? Think carefully about the steps required to get just halfway there. Keep learning, keep confidently plotting your points, and thank you so much for joining me on this explainer. See you next time.